The way I think of it, meaning this loaded solid body, is I think of it as a system through which stresses are flowing from the applied forces to the forces that hold the body in place. And I have an entire movie of how the architecture of the loaded solid body evolves. It is a movie consisting of 4 frames. The body is a cantilever beam, and here I will sketch very simply the 4 frames of the movie. In the first frame, the beam is, of course, implanted into a wall here. And it is the simplest design one can imagine, namely a beam that's cylindrical and with solid cross-section. This is the oldest kind of beam. It comes from the trunk of a tree or from the big branch of a tree. So the beam is loaded with a vertical force called the P at the end. It has a length L. In fact, the length is, as you'll see very soon, measured from the tip to the armpit, where the length is L. And it has a diameter D, which is constant. This is the so-called first frame, number 1. This is frame number 1. I will sketch the subsequent frames as I get to them. The thinking, in fact, this is the thinking behind all such designs, is that there is a function or a need for this member to provide to the larger flow system that uses this solid member. Let me make a more fundamental comment. The course until now was about flow systems that are visibly flowing, fluid flow through ducts, heat flow through leaky spaces, solid or fluid. All those flow systems had drawings consisting of solid parts, solid walls for fluid flow, the solid wall through which heat is leaking, and the reason, meaning the unspoken part of the lectures that you've heard already, is that, well, for fluid to flow, there must be a confining flow architecture, one that is solid. It is loaded with forces. It is, in fact, responsible for everything that flows through the greater body that carries these minuscule flow systems. Remember the vehicle that carries everything that flows? That vehicle is itself a propelled body, one that is on one hand propelled, on the other hand it is restrained by the drag that the environment poses. So here is the propulsion, here is the drag. And those forces impact, not to mention gravity, the weight of the body. Those forces are distributed throughout the body, including they're distributed through the structure that confines the more common, the more visible flow through pipe and heat leak through fluids and the solid walls. So this topic, the flow of stresses through loaded solid structures, is extremely important. The phenomenon itself is everywhere, and the phenomenon of the evolution of such structures is everywhere as well, not only in engineering, speaking about the evolution of vehicles, It is in the evolution of the skeletons of animals with locomotion. For example, the bones of birds. We'll get to the bones of birds in just a second. So the topic is extremely, extremely important. Now we start with the first screen in the movie plot. The cantilever beam. The cantilever is a very old word in Western civilization. It means lever, a solid piece with which you lift something, and canti means accanto, which in Italy, where a lot of this architecture comes from, it means supported from the side, canto. So there is a load, and the beam must not deflect too much. The beam has to be stiff enough. But in engineering, we call that stiffness, we call it strength. Now, quantitatively, the stiffness is the allowable deflection that the beam can have. We call this the deflection of the tip delta. So the so-called duty of the design is to have this delta subject to this loading. If you think of a spring that's being deflected, this is the elongation, this is the force that does the pulling. So you can think of P over delta as the spring constant. As I said, this basic way of thinking is in engineering. It's called strength of materials. It is a misnomer. It should have been called the stiffness of loaded bodies. But you understand. Now, the next item of reality is that the beam does, especially one that does this for humanity, doesn't grow on trees. Never mind my introduction with the wood from the tree trunk. This beam has to be made, and coming up with a material is not an easy matter. So the volume of the system, I call it V1, is it costs money and ingenuity in manufacturing. That volume is of the size pi over 4 b squared times L. The question that we will be answering very soon is how much of this material do we need in order to satisfy these requirements? There's a third requirement that you'll see very soon. It has to do with the fact that the material itself, wood or metal, is, every material has a property called maximum allowable stress. In the book is called S sub MA. This is a number of newtons per meter squared. A stress, this is force per unit area, that's not to be exceeded by the stresses throughout the body. So the stresses throughout the body should not exceed this allowable threshold. So that is the beginning of the lesson. Of course, the things I'm putting here, in fact, introductions to how to solve the problem. What stresses? Well, here's the object again. And with a load at the free end. And I said already that the stresses are inhabiting the whole body. Well, now, in fact, 200 years later, we take stresses for granted as being something internal. We use stresses as metaphor in describing the state of tension of an individual under threat. This body is an individual under threat, but the concept of stress is not to be taken lightly. It's a theoretical idea. It's just like the flow of heat. You do not see heat flowing. You cannot photograph it. It's the same with stresses inside a solid body. The stresses, like the heat current, are in the mind of the thinker. And that thinker was Bejan, a contemporary colleague of notable people such as Navier and Poisson and Fourier. Fourier, in fact, probably more so than all of these. And around 1825-30. And some of them came up with this brilliant idea of imagining a cut. The beam is cut, and meaning a cut into two pieces. So here is the stump, and the piece that is to the right. And hanging in the mind of the thinker. But wait a second, this piece that is to the right is not going anywhere, and that means that that piece, as imaginary as the stump, is subjected to forces that are in equilibrium. That means that in the vertical direction, in the cut, there must be a shear force of size P. The shear force, of course, has to be acting on the mating face of the stump. The so-called hanging part would be turning because of this moment of P times X. X being the arm of that force P, all the way here. So the next aha is that on this face of the chunk, there is a moment which we will call very soon M as a function of the location of the cut, a moment of the same size M but of opposite sense. The necessary thing about equilibrium is that the same moment M must be acting in the opposite sense again on the stump. Of course, you'll get the idea that the same moment is of course acting in the armpit, and so this is the method of imaginary cuts or sections of Bejan. I mentioned the name of Navier. To alert you to the fact, obviously, as I like to repeat, I'm teaching convection heat transfer next fall. It is course ME 532. And in that course, I'll talk about convection and the scientists who invented the field. And most important are these two names, Fourier for heat convection and Navier for the equations for fluid motion, which are known these days as the Navier-Stokes equations. Even though when Navier and his colleagues published those equations several times, Stokes was 2 years old. So Navier is the key name in that particular course. All right, so we are here at this image where the thing that all of us learn in undergraduate mechanical engineering is that this bending moment in the cross section, for it to exist, there must be, meaning for it to have this sense, there must be forces in that cut that that are responsible for these turning effects. Anyway, those forces are of tension in the dorsal fiber and of compression in the ventral fiber. You also learn in undergraduate strength of materials that these stresses are distributed linearly in the cross section. In fact, let me draw it this way. I'll blow this picture up here to show better the linear distribution of these stresses. There is a dimension called y that's transversal to the beam. Obviously here it's y equals 0. And clearly y equals d over 2. And then y equals minus d over 2. The stress that depends on the location y, namely S at location y, is varies, as I said, linearly, and its highest value, called Sn, is the value of S at the upper fiber, or for that matter, at the lower fiber as well. So we can say that S over Sm, which is a function of x. This, by the way, Sm is a function of S, as we'll see very soon. So this ratio is, because of the linearity, the same as y over b/2. The bending moment is itself a function of x, so it is 0. Another thing is that let me not go too fast. So I'm not going to redo the undergraduate course of strength of materials. The formulas that follow from analyzing this sort of a distribution of stresses, this distribution must match they must create a moment that matches this particular moment. From that, one arrives at key formulas that I will not derive. One is the formula for this SM. In the book, it's called max, actually. Max. The formula for the maximum stress, the one in the upper or lower fiber, is the moment itself divided by the geometric parameter called area moment of inertia of the cross section. So that's I1 in this case, and then Y max. The area moment of inertia is as a definition the integral over the cross-sectional area. Here's the cross-sectional area. Of y squared dA. In fact, let me draw that cross-section this way here. And if in the cross-section y is measured vertically, then dA is this area element, and y, of course, is the distance through it. Clearly, the calculation doesn't have to be carried over the entire cross-section. It's because of the y squared, it's enough to integrate from 0 to b/2 and multiply the result by 2, and you obtain the value of I1 for the round cross-section as being equal to, I added here, pi d1 to the 4th over 64. In the textbook, there's a typographical error. In the textbook, this equal sign is mistakenly missing from equation 10.2. So if you have access to your textbook, go ahead and make the correction. So what we have here is a complete picture of how the stresses at any location, namely this particular one, at location y in the vertical direction and x in the horizontal direction, how these stresses vary. So here this S is a function of x and y. In other words, let me summarize the conclusion that the stresses depend on x and y. They're equal to S max, which is a function of x, and then this other ratio, which is a function of y. S max is a function of x, is shown here as linear in x. I write it px over I1, and then y max. Y max is constant because it is equal to d/2, and this x here is a variable, just like y. And this formula tells us that the stresses that inhabit this cylindrical body are not distributed uniformly. Here's their distribution. All the stresses must be 0 at the free end. And they must be the biggest at the implanted end. So if x equals 0 here and x equals L here, the highest stresses will be in the plane of implantation. Furthermore, in the cross-section, as you saw, the stresses are distributed linearly. So that means that along the upper fiber, if you rotate the larger stress this way, on the upper fiber you have a distribution of stresses that's linear from the tip all the way to the armpit. So if that is S max, then the value of S max in the armpit is the maximum allowable stress. The same goes, the same holds for the compressive forces on the ventral fiber. Here it would be, let me make a drawing that's closer to reality. Okay, so maximum allowable stress for compression, for tension. The important conclusion here is that the stresses near the tip are 0. In fact, they are 0 famously along the center line, or the mid-plane. So S equals 0. From this we get a hint that for a solid cantilever beam, or in a solid cantilever beam, a lot of the material is really in for a free ride. It is not being used to carry the load. That material is in this trumpet-shaped area. And as we'll see very soon, the evolution of the design historically has been in the direction of avoiding such material, meaning using that material for other applications. Now, what happens, because we're interested not in repeating lessons from the past, we're interested in how much we have to pay. Meaning, what is this value of the volume that's required in order to satisfy these specifications? Now, there is a general formula in strength of materials which yields the value of the deflection of the tip. The deflection of the tip is a aggregate result of the stretching or compressing of all these fibers inside the body. Half of them in tension, the other half in compression. So the integral, the volumetric integral of those elongations or shortening is the value of delta. And so the general formula is delta equals the integral from 0 to L, meaning along the volume of the beam, and then the bending moment M divided by E times the area moment of inertia of the particular cross-section, which in general is a function of x. Not in this case, but in general it could be a function of x. And then the derivative of M with respect to P. Here, that would be an easy thing to calculate. It's called derivative of n with respect to p is x, and then dx. This is a general formula that in the book is called equation 10.5, and we will be invoking it basically 4 times. The first time is for this design, and that formula, because as I said, the n is px, partial of n with respect to p is x, and in our case, I is a constant. For this case, the delta, the deflection at the tip, turns out to be p L1 cubed. By the way, this length of the beam for design L1 is called, for design 1 is called L1. The diameter of the beam for this design is called D1, to be distinguished from subsequent designs that are more intelligent, you see. And then divided by 3e, and then I sub 1. E is a property of the material, which is elastic. So body is elastic. E is the Young's modulus. Modulus of elasticity, you know, this is the proportionality constant in Hooke's law. Who was Young? Young was Thomas Young. He was a very famous English polymath who made many and very lasting contributions, one of them being the invention of the word energy to cover in thermodynamics, and the physics after him covered this concept of the ability of a body to do work, which was known in mechanics, but Thomas Young was contemporary of these scientists that I mentioned previously. So basically, we have in this treatment we'll have 2 important formulas. One is this one. Let's call it Roman 1. The other important formula is the one for the maximum allowable stress, the one shown here, which is in fact well written already, but we can substitute. No, this is the stress along the upper fiber. Here you put d over 2, but the maximum allowable stress is in the armpit. So I made this. I will make this statement particular and write it right here that SMA for this design equals PL1 over I1, and then D1 over 2. So this is the second important formula. I use this notation to draw your attention to the fact that the analysis which happens for this design and subsequent designs has a template, and that template consists of 2 equations, Roman 1 and Roman 2. Roman 1 in the book is equation, where is it? Well, I did not make it particular, sorry. This is the general version. 10.5 is general. If we execute this integral for our case, we get the delta is equal to P L1 cubed. I already wrote it here, sorry. So that's the That's the Roman one according to the template. So there are two important formulas, and what's left is to use them in order to evaluate the necessary volume of material. And that volume of material turns out to be, so using 1 and 2 to eliminate D1 and L1. Eliminate D1 and L1 from this formula for volume D1. One obtains V1 equals 12. And then a group of quantities that altogether form a constant group. So the answer to the question of how much material should be used is right here. The group here is constant, as always, the question is, can you do better? To do better means to decrease this volume. How do you decrease this volume requirement? You decrease it by buying a stronger material, stronger. If you cannot buy it, then you have to invest in research and investigations to create stronger materials. And of course, if the load is bigger, you need more volume, and you can do your own thinking. The point is that you're actually stuck with a kind of material and with these three things here: material, load, and deflection. So the challenge to the thinker is to decrease this factor. Make it smaller. How? How? By eliminating the material that is not being used. It's like having 8 athletes rowing in a boat, and the coach notices that 2 of those 8 are actually not pulling. If the coach is any good, then the coach, he doesn't throw them overboard. That may have happened in antiquity. The coach replaces those with the 2 better athletes, or the coach is also better off by simply running the boat with the ones who can actually pull the lighter boat, you see. So the next design, which is inspired by this image, is called the number 2, of course. And I'll make that drawing to look like drawing number 1. Design number 2. By the way, before I continue, let me confess that this analytical treatment is valid for a particular limit of cantilever beam design, which is the limit of pure bending. That limit is spelled out correctly in the text, so please read that and review things you learned earlier in engineering school. Pure bending means that the beam is slender enough so that the stresses in the cross-section are due mainly to these things that I've been drawing, namely the tension and compression, meaning greater than the shear stresses associated with with the vertical force P felt in the cross-section. So pure bending is the limit in which this analysis is valid, and the analysis is valid, meaning the definition of this is such that L1 over D1 is of order 10 or greater, meaning beams are slender, more slender than the ones I've been drawing. All right, so here we have a new design of length L2 and diameter D2, except that the material that hugs the center line has been removed. The new beam is hollow. Here's a vertical cut through the beam showing the thickness of the tube wall. So now it's a tube. Here's that tube wall again. The wall thickness is called T. In the analysis that I will summarize next, it is assumed that large or small, the cross sections are geometrically similar. In other words, T scales with the diameter, and that ratio, I think that's how I defined it. I actually defined it relative to the radius, not the diameter. That ratio is a small number called epsilon, which in my numerical results was assigned the value 0.1. So that's a constant. So for this second design, the template analysis is repeated identically, and the object of going through the analysis will be proposed to you in one of the homework problems, namely problem 10.6. And that analysis yields, in other words, the job of eliminating, in this case, eliminating L2 and D2 from the formula for the volume. The formula for the volume D2 is obviously the solid material, which is pi D2 for the perimeter, and then times the thickness T, and then the length L2. So eliminate those two things by using or invoking formula 1 and formula 2, except that in this particular design, formula 1, which is this one here, is PL2 cubed divided by 3EI2, where I2 for a annular ring has a simple formula, namely I2 equals pi R2 cubed T2, or of course R2 is D2 over 2, or pi R2 to the 4th times epsilon. And then the formula Roman 2 is SMA, meaning instead of this formula here, SMA, the maximum allowable stress in this design is PL2 divided by pi, and then R2 squared T2. So that's the path to the solution to the problem, and out of that, meaning out of the template, comes the formula for V2, and that formula is turns out to be in fact, let me rewrite this definition as pi, and then the 2 R2 P L2 is the same as 2 pi, and then R2 squared times epsilon L2, and after you use 1 and 2, you discover to your great satisfaction that this assumed small ratio epsilon disappears. Epsilon vanishes because, you see, by postulating that all cross-sections, large or small, are geometrically similar, that means that you have deprived yourself of a degree of freedom called epsilon. So that has to disappear, meaning epsilon is not varying. And so the formula that emerges is 6, and then EP delta over SMA squared. This is the new cost of the beam, new compared with the previous. The previous cost was had the value 12, not 6. So the news, the reason to boast and to be forward-looking in your own thinking about this sort of domain is that by recognizing or giving yourself the freedom to change the internal structure of the beam, you rewarded yourself with a reduction of a factor of 1/2. In, you name it, the material volume or manufacturing cost or the cost of buying the metal or whatever it is, a 50% reduction is dramatic, or call it monumental. It is monumental because the first design, which comes really from prehistory, was incipient, which is the opposite of mature. It is a design that's asking to be improved. We'll see very soon, meaning in the next lecture, that nature itself improves this beam in the design of the branch of any tree you want. The branch is tapered at the free end, meaning it doesn't have a x-independent cross-section, even though the cross-section is solid. So freedom gives you these monumental surprises in the beginning of the evolution of the design. So at this stage, I think it is important to take a breather and recognize what I have introduced. it's not one stressed body. It is a class of such stressed bodies. Why a class? Because coming with this first drawing is my freedom to change the drawing. What is not changing is the duty, namely the force and the deflection and the kind of material. But the rest of it, the rest being the external shape and the internal structure, those are up to me. Okay? And these first two frames of the movie, first of all, I changed nothing, and then I hollowed the rod. You'll see in our next lecture that obviously the next move is to taper, to make things to vary in the x direction. I begin first of all with a graphic summary of what I presented in the previous lecture. That was a sequence of five configurations in the evolution of the cantilever beam. The first one was the solid rod with obviously uniform cross-section and obviously no internal structure. One competing design later on, as our thinking evolved, was the tapered solid beam, also solid, and you can see it here, thinner at the end. Competing with those two was the hollow tube. Here you have a cross-section that's annular. And then almost finally was the tapered tube. Now, there's another one that I will sketch next. The main idea is that in going from the simplest and the oldest, that took place through an act of allowing the configuration to morph. And the morphing had to do with the external shape, or shaping. In this process, as you saw in the calculations that I put on the blackboard, the volume of material required here decreased by 8 units. It decreased from 12 to 4. So 8 units saved. In this other direction, where shaping did not happen, but the internal configuration of the body was changed. I call this hollowing, or giving the object structure. Or structure. In this direction, 6 units of material volume were saved. Then this fourth configuration was accessible in 2 ways. One was by hollowing the tapered solid beam. In that move, 2 units were saved. Or the same object arrives on the right-hand side by taking the hollow tube and giving it a tapered shape externally. So that means shaping. and this yielded a savings of 4 units. So there's more than one way in which to evolve the configuration, but the direction is toward lighter and lighter. The fifth configuration that we analyzed in the previous lecture was the beam, tapered as it was, but with a cross-section that was essentially a North Pole loaded fiber connected with a web to a South Pole fiber that is in the cross-section. That is, well, anyway, this is the view in profile, but you can understand that the cross-section is also like the one shown above, namely annular, except that in the center there's a web that's of negligible weight. This is the very classical now I-beam profile. You find it in many places as an I-beam cross-section, or as the cross-section of the rail used for trains and other such rolling equipment. The foot of the cross-section is wider for the purpose of bolting it down to the ground, and there is the L-shaped profile and some other profiles that approximate this sort of idea. And in any case, the evolution from the previous champion to the next consisted one more time of doing both things, shape externally and structure internally. And this yielded a savings of 1 additional unit. That is, 1 additional that compared with the previous winner. Now, the bottom line, by the way, this tableau is from my new book, Freedom and Evolution. Which is the supplemental reading material for the course. It is from page 127. The message of this bird's eye view is that with freedom to change the design, one has more and more access to better performance. However, in the same happy direction, a phenomenon of the decreasing savings is taking place. The bigger savings happened when this idea of liberating the architecture was implemented first. Here. Later, when the idea was no longer new, and tried again here, the savings turned out to be smaller. And then, by the time the idea became mature, additional, let's say, compounded applications of that idea led to even smaller savings. So, hand in hand with the greater freedom, continuing evolution and increasing performance, yes, because these these savings are occurring in the correct direction. We have from physics, the physics of evolutionary design, we have the emergence of this physical phenomenon of diminishing returns. And the returns are becoming smaller and smaller. In this direction, the cross-sections may change, but they do not change much in order to look different. So after many, many invocations of these ideas, the design itself arrives at a configuration that seems to be unchanging. So, but that's an illusion. In any case, it is a correct impression, which is that the evolution has stopped. Not true, but that's the impression. Has stopped. I put it in quotation marks. That impression is the name of a mature design. Mature design is the configuration of all these animals that's running on a landscape. They've evolved for millions of years. They give the impression that they are not changing, and they invite the observer, especially the professor of biology, to teach that evolution in biology is not observable, because, meaning macroscopically, because it has taken a long time. Well, that is true, but evolution, of course, never stops. And so that's the first lesson from this particular topic. And now the conclusion to the lecture. When it comes to usefulness, if you have an idea, it's just like when you know a good song, you sing it, you hum it many times. When you have a good wine, you taste it more than once. It's the same with this idea of achieving greater performance in the case of a solid body loaded with function, greater performance by giving it more freedom. And where you stop on this road to to paradise depends on the time you have, the patience you have, and to what extent you don't have better ideas to distract you from falling victim to this mirage of which turns out to be diminishing returns and mature design. Mature design is an important concept. It means this, that if the hollow tapered tube for a beam is what you can design more cheaply, because it's got this body of revolution configuration, like the top of the big pen, then that's probably good enough. Meaning not everything has to look like the I-beam profile. So mature design is a wide, very wide world of designs with comparable levels of performance. And in that world, some of the designs are obviously a little bit older, meaning less refined, but almost as well performing as the finest and the fanciest and the most expensive. So keep in mind that freedom, big word, takes you not only on this road to paradise, but also means that you have the freedom to decide when to stop. And on that note, I decided to exercise my freedom and stop right here. Until next time.